Now we look at some example. So this is a power series, okay, about -1. X minus x0. X0 is now -1. Okay, the coefficient an is 1 over n 2n. Okay, then we study whether this power series converge, and if it converge at some the radius of convergence. Okay, so we consider the limit for computing the radius of convergence. So this limit is easy to compute. An is 1 over n 2n, and an plus 1 is similar. Okay, then this limit is 2. Therefore, the radius of convergence is 2. So the interval of convergence is an interval center at -1, which radius 2. Therefore, this is -1 minus 2 minus 1 plus 2. That is -3 1. So this is the interval of convergence. This is an interval centered at -1, which is range 4. Okay, and we don't know whether the series is converge at the endpoint of this interval of convergence. So we need to study the convergence of the series at the endpoint. So when x equals 1, the series is sigma 1 over n. This series is diverse. Therefore, and when x equal to -3, the series is -1 to the power n over n. This series converge. Therefore, we conclude that the domain of convergence is -3 1. The interval, half open interval, which is closed at the left endpoint and opened at the right endpoint. Okay. And when dealing with power series, we will always use the shift of index technique. So consider this is power series from n is from 2, because the power of x minus x0 is n minus 2. Therefore, when n is 2, this is the power is 0. Therefore, this is the constant term. Okay. So, but we want to write it as the term from 0. So we let n minus 2 to be k. Let n minus 2 to be k. Then n is k plus 2. So substituting n equal to k plus 2, then n from 2 to infinity means k from 0 to infinity. So this series can be written in this way. The range of k is now from 0 to infinity, and the coefficient, the power of x minus x0 is now k. Okay, because n minus 2 is k, and the coefficient. The original coefficient is n plus 2 multiply an. Substituting n equal k plus 2 into the expression for the coefficients, we see that the coefficient of x minus x0 k is k plus 2 for a k plus 2. Okay, so this is a typical example of shift of index. Another example, we consider this x squared multiplied this power series. Okay, here r is an integer. Then, because x squared does not depend on the summation index n, we can move x squared inside and combine the power of x squared with the term in the power series to get this. So this is r plus n plus 1, because minus 1 and plus 2. Okay, then this is r plus n plus 1. Okay, combine the power of these two terms, we get this term, and the other part copy. Okay, now we want to change the index here. So let n plus 1 to be k. N plus 1 to be k. Then n is k minus 1. So this can be written as r plus k minus 1, because n is k minus 1. So r plus n, the coefficient r plus n become r plus k minus 1. And the an is ak minus 1. And the x r plus n plus 1. N plus 1 is k, therefore the power of x is r plus k. And the range of summation, the original summation is n from 0 to infinity. Therefore, correspondingly, k is from 1 to infinity. So this is also shift of index. Okay. Now we consider this example. Suppose a power series sigma an xn satisfies this equality. We are required to determine the an. Okay. So how to determine this? So by assumption, the sum of n from 0 to infinity xn is the sum of n from 1 to infinity n xn minus 1. The trick is to write the right hand side to make the power of x to be the same as the left hand side, that is n. So we let n, for this purpose, we let n minus 1 to be k. So the right hand side can be written as, by the shift of index we just discussed. This is n is k plus 1. So the right hand side is k plus 1. ak plus 1, xn minus 1 become xk, and n from 1 to infinity correspondingly k from 0 to infinity. So these two, the right hand side can be, we can replace the k by n, because in the summation, which letter is used to be the summation variable or summation index is not material, not essential. You can change it, use another letter to denote the summation variable k. So we use n. So this can be written as n from 0 to infinity, n plus 1 an plus 1 xn. Now comparing the left hand side and the right hand side, the coefficients of the same power of x must be equal. Otherwise, this equality could not be true. So we see that an equals n plus 1, an plus 1. So using this, we see that an equals 1 over n, an minus 1. As long as n minus 1 is non-negative, we can apply this again and again. So this becomes an minus 1 becomes 1 over n minus 1, an minus 2. Okay. So apply this again and again. Finally, we will obtain the 1 over n and a0. So this is the formula for an. So substituting the result of an into our power series, suppose the power series, the sum of the power series is fx. So fx is an xn, n from 0 to infinity, and an is given by this formula. So we obtain this. But this sum we know. That this is precisely the exponential function. So we conclude that the sum of our power series is exponential function. Okay. Now we start our study of series solution for second ordered variable coefficient linear equation. So the equation is of this form. The coefficient of the derivative of y and y itself depends on x. They are function of x. And in general, this is a non-homogeneous equation. But for simplicity, we only consider the case that f is 0. That is, we study homogeneous solution equation only. The case for non-homogeneous equation are the same. You expand fx in power series and then compare the coefficients. Okay. So for simplicity, we only consider the homogeneous case. And here is some example. Sorry, this is y prime. This is a misprint. So this equation is called the Bessel equation. We will study this equation in detail later. And also we have the Zander equation. The Zander equation is of this form. So we found that the coefficient of y double prime and y prime are functions of x. And of course the coefficient of y is a constant. It is a parameter alpha. Does not depend on x. Okay. So In this part, we study the case that PQR are polynomial. We study polynomial coefficients first. So both our this Bessel-Fang equation and the Legendre equations, the coefficients are polynomials. Okay. So we have a function, we have a coefficient in front of the second order derivative. But we want to make this to be 1. Therefore, we want to divide both sides on the equation by px. So, but if px is 0, we could not divide px on both sides. So we need px to be not 0. So for this purpose, if px0 is not 0, then such x0 is called an ordinary point of this equation. For polynomial coefficient equation, that is PQR, are all polynomials. If px0 is not 0, we say that x0 is an ordinary point. Note that this concept of ordinary point only apply to polynomial coefficient equation. If PQR are not all polynomials, one of them is not polynomials. So for those equations, we do not have an ordinary point. We do not have the concept of ordinary point. Ordinary point only applied to polynomial coefficient equations. Later we will generalize this concept to a slightly larger class of equation. But currently we only discuss polynomial coefficient equations. Okay. So px0 is not 0. So x0 is ordinary point. By continuity, we know that p is not 0 in a neighborhood of x0. So because p is polynomial, it is continuous. A continuous function is not 0 at some point. It will be not 0 in a neighborhood of the point, near the point. It is still not 0. Okay, so px is not 0 near when x is close to x0, or x is from the small interval of x0. Therefore, we can divide the equation by px to obtain a new form of our equation. Rewriting the equation in this form. Here, the small p and q. Small p is the the original coefficient of y prime divided by p. We can divide it by p because in the neighborhood near x0, p is not 0, px is not 0. Therefore, we can divide this, okay, by p. Similarly, small q is r divided by p. So both small p and small q are continuous functions in the neighborhood of x0. So we are looking for solutions of the form of a power series. So how to find a solution of this form? So solution of these forms are called series solutions. The series solution has some advantages. Firstly, for variable coefficient equations, you are not always possible to find a very elegant form of the solution. So you have to use series to express your solution. Only for the constant coefficient case, we can have a very elegant, very beautiful result for beautiful expression for the solutions. But for variable coefficient case, sometimes you have to use series. Okay. Secondly, is that series solution, although looks ugly, but they are easy to manipulate. The computation and are easier for dealing with the series solution. Of course, the series solution contains infinitely many terms, so you could not compute infinitely many terms. But we can use the partial sum of the series to approximate the solution. Okay, as a partial sum, the partial sum of the series solution is a polynomial, which are easy to compute. Okay, easy to study analytically or numerically. Okay.